Hello again, astronauts. Welcome back to my channel. If you're new here because of the fat phobia video, welcome. That video required months of research, intense planning, and we're getting married. Well, we're already married, but we're having a wedding in January, so I just do not have the spoons for that this month. So we are going to be doing a deep dive into the science of our favorite TV show, The Expanse. Because this is an Expanse stan channel now. We'll continue to put out high concept scientific deep dives into important topics after our honeymoon. So for now, we're just gonna do some fun little science videos and get excited for season 6 of The Expanse.
Yeah.
From the opening scene, we know that The Expanse is going to be a different type of sci-fi show. Through clever wire work, camera angles, and CGI, we see that this show is going to take physics seriously. Specifically, gravity and acceleration, and their real-world consequences. Say goodbye to inertial dampeners and artificial gravity, because we're exploring the expanse of space. And it's terrifying.
Now you need to ask people for money.
Oh, yeah. I have some quick housekeeping. In order to keep doing these episodes, we do need to pay for things like costumes, equipment, locations, etc. I have a nice ring light. I have a nice microphone. Those are paid for by our lovely patrons. All of the awesome stuff, especially for the fat phobia video, is thanks to our lovely patrons. Please join our Patreon if you want to help us keep bringing you awesome science. We also have a lot of perks for patrons, including behind the scenes, the blooper reel to this video, which since we just filming, I promise is going to be quite extensive. You get production updates at every level. At the higher tiers, we do video podcasts once a month. So there's so much extra fun stuff and ways you can get involved with this channel. We are also sending out holiday cards to all of our patrons to show just how grateful we are to all of them for making this possible. There's going to be a picture of me, Nova, Cece, Eris, and Science Tommy on them. If you join our Patreon by December 15th, we will send you a card. December 15th is the cutoff. So you can get them by Christmas. I know, hashtag war on Christmas. We didn't have our stuff together enough to send them out before Thanksgiving or Hanukkah. Sorry, everybody. But you will get your holiday cards by Christmas well, according to the USPS. That's all the housekeeping we have to do.
That was like 2 minutes of her asking you for money, so I'm sorry.
What if Cece asked for money? Do you think people would give her money? She's really cute. She's so cute. Give me your money. My mom will spend it on videos. Hey, girlie. Hey. Right, video. We rewatched seasons 1 to 5 of The Expanse in preparation for season 6 dropping, and decided to review several major science choices the show made, and go into the science behind them. We will try to keep this as spoiler-free as possible to those of you who haven't seen the show yet. So, if we leave out character names or give very little context to a situation, that is why. If you hadn't noticed, this is an Expanse stan channel now.
Yeah, screw high-quality, well-researched, high-concept content.
We're planning a wedding. I don't have time for that. Number 1, the flip and burn.
This will be a high-G maneuver. Prepare for flip and burn.
The flip and burn is a description of how ships in the Expanse change direction. They kill the engine, use small thrusters to reverse the direction of the ship, the flip, and then reignite the engines hard, the burn. On the inside of your ship, the crew will feel briefly weightless before gravity returns with a vengeance. Depending on how hard you burn, you can kill your crew. Why would changing direction and speed have fatal consequences? There's nothing to crash into. It's space. Let's talk about how acceleration mimics gravity. Say you're in a closed elevator, sitting still on Earth. Gravity, the force, pulls down on you with ma, or your mass times the acceleration of gravity, g, or 9.8 meters per second squared.
At least on Earth.
Yeah. G, the acceleration on Earth is constant for everything on the surface of Earth, and it's 9.8 meters per second squared.
Lowercase g. Uppercase g is something different.
We don't talk about uppercase G in this. So you're standing still in this elevator with gravity pulling down on you with force equal to ma. But you don't fall down to the center of the Earth because the elevator floor pushes back upwards with a normal force, which is going to be equal to that exact same ma, or 9.8 meters per second squared, the acceleration, times whatever the mass is, mass. You don't really feel the pull of gravity ever. What you feel is the normal force of the elevator floor. So when you're in a gravity well, what you are feeling is the upward force, not necessarily the downward force. It just feels like downward force.
The big point is that when you are in free fall, you feel weightless. So for example, the astronauts on the ISS don't feel weightless because they're so far away from Earth that they're not feeling the Earth's gravitational pull. In fact, the entire International Space Station is orbiting the Earth, which means it definitely feels Earth's pull. It's falling toward Earth. The thing is, it's falling toward Earth constantly. It's moving so fast to the side that instead of falling down onto the planet, it falls continuously around the planet. And so, because they're in continuous free fall, they feel weightless, even though, technically speaking, they are not avoiding all gravitational fields.
So how does that work if they're orbiting a flat Earth? Am I sleeping on the couch tonight?
Actually, there was someone who went and calculated just what things would be like if we lived on a plane, but gravity still worked the same way that it does in our actual world.
Mm-hmm.
And you get some really weird shit when you got to the edges of the planet.
I mean,
Like, you wouldn't...
yeah, wouldn't it feel like you were being pulled to the side rather than...
Yeah, it would basically be the edges of the planet would feel like they were uphill and then going toward vertical. Because you'd be pulled
that would
toward
make sense
because gravity pulls you toward the center of the mass.
Yeah.
And so you get pulled back toward the middle of that plane. So you wouldn't fall off because you have to climb out.
So you're not walking to the edge of the Earth, you are climbing up to the top of the Earth, but the top of the Earth is in every direction?
Yeah, basically. So I think it would feel like you're at the bottom of a big cup, like, or a big semisphere.
What I'm hearing is that there needs to be a theme park at the edge of flat Earth where it's just like a Rodelbahn. Like, it's just a little slide.
Really big roller coaster.
Really big roller coaster.
I like it.
I like it.
You don't have to just have it on the edge of Earth. You could have an Earth-long roller coaster.
Earth.
And do this.
Long roller coaster. That's brilliant. I would like to make it clear we are joking. The Earth is a globe. This was a joke. The Earth is not flat, it is a globe. Okay, so we're standing in an elevator, no windows, no doors, in Earth's gravity, and we feel that normal upward force on us. Now, imagine you're sitting in that same elevator, but instead of on Earth, you're in the empty void of space, accelerating in some direction at g, or 9.8 meters per second squared. There's no gravity acting on you, but the floor of the elevator is still exerting the same force, 9.8 meters per second squared times whatever your mass is, on you. Assuming you have no windows to see out and there's secure atmospheric containment, you have no way of perceiving that you aren't just sitting on a stationary elevator on Earth. Unless you're accelerating in a weird direction and the wall is now the floor. So that was a fun thought experiment, but how is it related to a spaceship switching directions? Well, to simulate gravity, all we need is acceleration. A side effect of faster acceleration of your starship is a stronger perceived gravity. Our crew will always feel like gravity is pulling them in the opposite direction of the acceleration or towards the engines, because the ship is pushing them in one direction and their brains fill in the non-existent gravity. So, if you want the crew to experience 1G, or Earth's gravity, for most of your flight, just accelerate at 9.8 meters per second squared for the first half of your journey, flip and burn, and accelerate in the opposite direction at 9.8 meters per second squared for the back half. You'll be coming to a stop just as you arrive at your destination, since you speed up and then slow down by the exact same amount.
Deceleration is the same as acceleration. In fact, deceleration is a type of acceleration. So the slowing down is also going to make you feel that same force of gravity. Another cool feature of The Expanse is whenever they show ships coming into a port, they appear to be coming into port backwards. Sometimes they then do some weird, complicated turning maneuvers, also scientifically accurate, to get themselves lined up with the station or whatever. But the big point is that when they're getting close to something and they want to stop, they approach that thing backwards. The engine is pointing toward the thing they want to reach.
Because if you accelerate backwards, you are just decelerating.
That's how you slow down.
And it feels counterintuitive because we're used to a world with cars and ships with friction. So what we are used to is friction braking. It feels weird to think, oh, well, if you're driving down the highway at 70 miles per hour, what you really have to do is turn your wheels around and then speed up until you're going at 0. What you would just do is brake, right? Well, what are you going to brake against in space? When you brake with your car or with or with your bike or any vehicle on Earth, what you're doing is braking with friction and relying on the friction force of the ground to bring you to a stop. There's no friction in space. So half your fuel when you're going on a space flight is always used to slow down. Like, you can just be going too fast forever. That's a thing that could happen. So, if you want your crew to experience 1G, or the perception of Earth's gravity, for most of your flight, you just accelerate at 9.8 meters per second squared for the first half of your journey, flip and burn, and then accelerate in the opposite direction,
decelerate,
at 9.8 meters per second squared for the back half of the journey. You'll be coming to a stop just as you arrive at your destination, since you sped up and then slowed down by the exact same amount for the exact same amount of time. And you will have felt like you were in a building on Earth for all but the brief midpoint of your trip. The beauty of this simple symmetrical acceleration method is that you can pick any consistent gravity amount you'd like. But what if you need to get somewhere, or more to the point, the fuck away from somewhere, quickly? Let's talk about the side effects of rapid acceleration.
Up to 1G, humans are good. We evolved in 1G. So 9.8 meters per second squared, we're chill. Once you get to higher accelerations, things start to feel uncomfortable. So typically speaking, humans can survive in up to 3G for a few minutes. That's what astronauts typically experience when they are traveling up to, say, the ISS.
And remember, astronauts and fighter jet pilots all have extensive training and assistance from drugs to make that transition easier.
But when astronauts launch, they'll often experience 3G, and they're fine. However, once you get above that, the amount of time the human body can withstand at that high G starts to diminish. So up to 9G, you can survive for very brief periods of time, but 9G for more than a second and you're pretty much dead.
Yeah, fighter jet pilots, I think, can go up to 9G for, again, like a second.
Yeah. After that, you will pop a blood vessel in your brain, have a stroke, and die.
Foreshadow much? Spoilers.
I mean... The point is, in the real world, you cannot accelerate willy-nilly. That's important. In a lot of sci-fi, they use something like inertial dampeners, which is basically magic that says we can accelerate without feeling it, and it's fine. But in the real world...
Bug on a windshield.
And that means that you cannot accelerate too much. That also applies to any maneuver that involves spinning or turning, because that is also a form of acceleration. Anytime you want to change direction, anytime you want to speed up, anytime you want to slow down, there's a limit to how much the human body can take.
And as a result of this lack of inertial dampeners or space magic to make filming easier...
Plot happens.
Yeah. A lot of scenes that just wouldn't exist in shows like Star Trek or Star Wars or Battlestar Galactica, or really anything where they have artificial gravity and inertial dampeners, scenes that couldn't exist in any of those other shows happen in The Expanse, and they're some of the most high-stakes scenes of just people trying to survive in space, battling not even villains, but physics. And it's really cool. I really like it.
Flip and Burn gets an A.
Nice.
I
Solid
don't
A.
give A pluses.
She does not give A pluses. I have never gotten an A plus. Which means they don't exist. So, what if we're not on a ship, but a station, like Ceres? We don't want to keep moving, or we don't have enough fuel to keep accelerating for an infinitely long time. Like, there's a city's worth of people on Ceres. Well, acceleration doesn't just mean change in speed. It can also mean change in direction. So you mentioned that spinning and turning were another type of acceleration, which brings us to our second fun science thing about The Expanse, which is spun up asteroids. For example, in the opening episode at Ceres Station. So Ceres is an asteroid in the asteroid belt. In The Expanse, this future world, there are people living inside Ceres Station. Say you're floating in space, and someone comes along and builds a large cylindrical space station, complete with atmosphere, around you. How convenient! You can now remove your helmet, but you're still floating aimlessly in the center with nothing to grab a hold of. But then the station starts to spin. The spinning outside shell bumps into air molecules, which in turn bump into you, and you start moving in some direction. It doesn't matter which direction, since you're inside of a spinning cylinder. All directions lead to the spinning shell. Soon enough, motion along any straight line will hit the shell, or the floor of this station. Your body wants to keep moving on that same straight line, but the floor pushes you back in another direction, this time tangential to the floor's outer spin. You'll get bounced along until you're brought up to the same speed as the spinning shell. But the tangential direction keeps changing because the floor's motion isn't a straight line, but a spin. Say I twirl a keychain around my finger. The minute I remove the inward force from my finger, the keychain flies off. For you, the astronaut in the spinning space station, that force is provided by the outer shell. Does Cece want the keychain now?
I think she's gonna go fetch it.
Go get it, Cece. Yeah. Go get it. Instead of being pushed outwards by the floor or the ground to keep you from falling into the center of the earth, you are being pushed inwards to keep you from flying off into the void of space. And the faster you're changing direction, so the faster the outer shell is spinning, the stronger the gravity you will feel. And just as gravity gets stronger as you get close to the center of mass, the simulated gravity, or spin gravity, feels stronger the further out from the center of rotation you get, since the same angular velocity will be a higher speed at a further radius, because a given point will have to travel a further distance in the same amount of time. This is, incidentally, how wheels work.
The entire idea of spin gravity is the same idea that you may have experienced on those sketchy county fair rides where they spin you really fast and you stick to the wall. If you've ever experienced that, apparently they don't have them in fairs much anymore.
They have them, but now you need to be belted in, which defeats the purpose.
Physics says you will stick to the wall. So, there's that. Now, it is a little bit trickier with that because there the spin gravity is pointing to the side relative to Earth's gravitational field. So you do need to make sure there's enough spin gravity such that friction keeps you from sliding down. Basically, friction is enough to overcome the external gravitational force of the Earth. On a station, that's not a thing you have to worry about because there's no external gravity that you are concerned with.
I remember going on one of those rides at a fair when I was a kid, and after the first 2 times, my dad refused to go on it because he was feeling a little woozy, but I went on like 10 times.
For those of you who've never had this lovely experience,
It's amazing! I'm so sorry.
you have also probably experienced this if you've ridden in a car and someone goes around a turn really quickly, and you, especially if you're sitting in the back seat, get slammed into the people sitting next to you, all getting crammed up against the outside of the turn.
This may be a later video, but we're still going after my father, apparently.
He gets me carsick a lot.
Leave it in! He watches these. The Expanse opens on Ceres, an asteroid that has been spun up with people living in tunnels on the inside. The down direction is towards the outside of the asteroid, which is why we see Miller throwing the corrupt air filter guy down into an airlock. Earthers fall down towards the center of the Earth. Belters fall down towards the void of space. This is why, when our crew are trying to get to the ship docks for spoiler reasons, they find a ladder and immediately go down.
I should also note that the reason they use spin gravity on an asteroid like Ceres is because while Ceres does have gravitational pull, it's pretty low mass, and as a result, the gravitational pull of Ceres is substantially lower than what you get on Earth, so much so that this spin gravity, which in universe is not enough to replicate 1g, it's more like 0.3g.
On the outside, yeah.
On the outside. While it's still only a small fraction of Earth's gravity, it's still much larger than what you would get with Ceres' natural gravity.
In the world of the Expanse, Belters live on ships and inside of spinning asteroids, and the ship's acceleration, or the asteroid's size and speed of rotation, determines the gravity they feel. Different levels of Ceres station have different felt gravities, and because of Ceres' speed of rotation, the simulated gravity is only about 0.3 g, or a third of Earth's gravity. Growing up in low G causes a host of medical problems for Belters, or people who were born in the asteroid belt, and most of them couldn't survive in Earth's gravity for an extended period of time. The Belters grow up taller, leaner, and physically weaker, to the point where on Earth, it's considered gravity torture to force a Belter to remain on the planet outside of a water tank. The show doesn't shy away from the quite dark ramifications of a society where class inequality has become a biological reality over a few generations, and the anti-capitalist politics of The Expanse are one of the reasons we love it so much. But this is a science channel, and I did an intense video last week, so let's take a break with something lighter. A noticeable Coriolis effect is a hallmark of this simulated spin gravity. When you drop something from inside of a spinning asteroid, it falls outwards, but the ground, or outside, spins enough underneath it that the object doesn't appear to fall straight downwards. The practical daily result of this is that on spun-up asteroids, characters pour coffee from off to the side of the cup, not directly over it. And when the crew is trying to get to the outside of the asteroid for spoiler reasons, Naomi tests their progress by dropping dust and watching it fall on a curved path toward the ground.
Now, I will mention that from what I've read, and I believe this, the Coriolis effect that they show is a little bit exaggerated relative to what it would actually be. So I'm going to give this whole thing an A- as a result.
I think it should be, but still in the A range, because I feel
Yes.
like that's artistic license.
Yes, they got all of the major physical plot points correct. It's just that the Coriolis effect probably wouldn't be so exaggerated.
It's the equivalent of having a fantastic essay with just a few minor grammatical errors and phrasing issues.
Yes. The other thing I'll mention is that the Coriolis effect is not limited to places with spin gravity. Anytime you have a rotating reference frame, Coriolis forces can be an issue. And in fact, on Earth, Coriolis forces are the reason why we have hurricanes and why hurricanes in the northern hemisphere and typhoons in the southern hemisphere go in opposite directions. It's because of the rotation of the Earth. You can see the effect of the Coriolis force in any rotating reference frame, but if you are not rotating as quickly, you will only see it on very large scales. So for example, the scale of a hurricane. There's a myth out there that toilet bowls flush in the opposite direction on the northern versus southern hemisphere. That's not true. The Coriolis force on those scales way too small relative to just the forces of your toilet dynamics. So that's not the case. However, you might see something like that on Ceres.
So A-?
A-.
Okay. Number 3, Newton's third law of battle. While in 0G and getting shot at for spoiler reasons, Holden and Naomi, two of our mains, lose contact with the floor and start floating away from a bridge they must cross. They're floating ducks without anything to hold on to until Holden tethers himself to Naomi, then kicks Naomi further away from the bridge, propelling himself backwards towards the bridge. He then engages his mag boots, introducing an outside force, and uses the tether to pull Naomi back to the bridge. They're still getting shot at, but at least they have something to hold on to now. Holden's quick thinking with this move worked because of Newton's third law of motion. For every action, there is an equal and opposite reaction. Holden and Naomi are floating, and Holden exerts a force pushing Naomi away from the bridge, our action. Because no other forces are acting on the two of them, the total momentum of this two-body system is conserved. So Holden's body is also pushed towards the bridge, our opposite reaction. Because Holden isn't that much bigger than Naomi, the force pushing her away is enough to quickly get himself to the bridge. Once Holden engages his mag boots, he can safely pull Naomi towards him. Well, as safe as anything can be while you're getting shot at. Now that Holden is connected to the bridge via mag boots, the reaction to pulling Naomi towards the bridge is not enough force to pull Holden off the bridge.
It's a very good, clean example of keeping the laws of physics in mind. And I would say, rather than talk about the finer details of this physics, I think it's important to compare this to one of the worst sci-fi moments I've ever watched, which is in Star Trek Into Darkness. Not a great movie to begin with. When the Enterprise is crashing toward Earth, it's in free fall, everyone should be floating, and yet somehow gravity just keeps changing and they keep getting thrown against different sides of the ship. You could make an argument for some sort of spin something, but it's tenuous at best.
I don't really understand how the inertial dampeners actually work in Star Trek, because every time there's turbulence, they shake, but then they can just, go to near speed of light on impulse and not be bugs on a windshield.
And in this scene, I'm pretty sure both the inertial dampeners and the artificial gravity were offline, and that was the point.
Okay.
Because everything was broken. However, despite this, gravity kept just changing. And again, sometimes if you have changes in direction, that's possible, but the outside shot showed the Enterprise just falling toward Earth. So,
Yeah.
Anyway, this scene gets an A.
Okay, now we're going to do the rapid fire speed round. So, number 4. Amos just has to walk 10 feet, or around 3 meters, to save another character's life. And it's a life-threatening journey because gravity is changing direction. But not for random Star Trek reasons. They're actually in a firefight, and the ship is flipping and burning and turning and spinning.
Lots of hard maneuvers.
And despite what really should be stronger OSHA regulations in The Expanse, but despite OSHA regulations, someone left a giant box full of farm tools unlocked. They attempted to lock it, it just didn't get all the way locked. We're not blaming one of my favorite characters, the biologist, but
I don't know, he was being pretty sloppy. If gravity is changing and there's shrapnel, bad things.
lock your farm equipment away so you don't get stabbed by it when your ship changes direction. Just lock it up safely. OSHA. This is the second video I've talked about in this. It is my favorite scene from The Expanse. My absolute favorite scene. I love it so much.
Apparently you give it an A. The science has done well.
I give it an A+. A+ for Amos's biceps. Number 5. Alex slingshotting around Jupiter's moons to avoid using fuel and being detected.
Really, it's not about whether he was using fuel or not. It's whether he turned on his main engine.
Yeah.
Because, again, that's how they detect you. Which, again, also realistic. Because your main engine is going to produce a lot of light, electromagnetic radiation, and that's how you're going to find people. Anyway, this one is okay. So the idea of using gravity assist is great. That is, in fact, a way that we get spaceships or really probes to other parts of the solar system.
Just probes for now.
Yeah, just probes for now. So when we send a probe out into space and we want it to get to, say, Jupiter, we'll often have it take this weird curvy trajectory because you're using the acceleration due to the gravity of other planets and celestial bodies to basically give yourself a little bit of a boost. That's real, that's good. The issue with that is the trajectory that he would have taken using the system of Jupiter's moons would have taken a lot longer than is portrayed in the show. So there's no way that he would have been able to get from where he started down to the surface of Ganymede, the moon that he was trying to get to, in time to be relevant for the plot.
Fun fact, the showrunners have already been thoroughly called out on this, and they have apologized. It means they really do take the science as seriously as we do, which is just, it's so lovely. What grade would you give this one?
I'd give it a B, B-.
Yeah, so good concept, whiffed a little on the execution.
Yeah.
B, B-. That is a Northwestern B, B-. It is a U Chicago C+, and of course a Harvard A.
U Chicago C.
U Chicago C, not even the plus?
Yeah.
Number 6. The effects of radiation poisoning. We're going to go through this really quick because a lot of you have already seen Chernobyl and we had a whole nuclear energy video earlier, but basically,
2 characters get irradiated and they are fine at first, but then start to show the symptoms of acute radiation poisoning. They get those symptoms right. It's good. Well, it's bad for the characters because acute radiation poisoning is really bad.
It's extra dead. Extra bonus dead. It's so dead. It's real bad.
But the way that, your skin turns red and blah, 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 the burns, all of the symptoms they do pretty well. It's not a huge point, but
well
go
done.
team.
Yeah. A.
Yeah.
Solid A. Number 7. Another contender for one of my favorite scenes and really one of the most shocking scenes. Like, my jaw was on the floor for this one. A character survives the void of space without a suit.
So I'm not a biology expert. I know that they did a good job from what I know of biology. But I don't actually want to comment too hard on this one because, again...
Spoilers.
Well, spoilers, and again, I don't know enough of the biology to really know how well they did and to
They showed
be a good
popped.
grader.
They
But-
showed popped blood vessels, which was
Yep.
great. They showed the character not being in the void of space for more than a few seconds. They show the character getting a shot of oxygenated blood to help them, and this was pre-planned, and it was kind of a moonshot of desperation. Don't go into the void of space without a suit. They also show a whole bunch of people dying in the void of space without a suit. That's
But it is important to note that unlike some pop sci would have you believe, when you enter the vacuum of space, you don't immediately explode or anything that gruesome. It is bad. Blood vessels do pop due to the pressure issue and the fact that, blood boils and all of that. However, you can typically survive in the vacuum of space for anywhere between 30 seconds to, I think, a minute and a half is what I've read. So the idea of having a character do this spacewalk without a suit, as long as it's very quick, is actually fairly accurate.
Yeah. And this character was not okay afterward.
Oh yeah, it don't try this at home.
This character was messed up and needed serious medical attention afterward.
But did not die.
Did not die. Correct. So I'm going to give this an A, but since neither of us are biologists, we're going to leave this to reviewer 2 to tear apart.
Yeah, I'm going to withhold a grade.
Yeah, fair. Moving on, number 8. A character dies of a stroke due to high G maneuvers.
We've already talked about this. You can only survive so many Gs for so long. The higher G the environment, the shorter the amount of time you can survive it. And sometimes you just get unlucky. Basically, high G means that your entire body is experiencing a lot of force that it's not accustomed to. And that includes all of the blood vessels in your body, particularly the blood vessels in your brain. If one of them pops at the wrong time in the wrong place, you get a stroke.
Yeah. And it is a risk for everyone. Obviously, the risk is higher for people who have not trained, for people who aren't using drug assists, but it is a risk for everyone. And the more you experience high G, the more risks you are taking. Give that one an A. And by the way, I am not using character names for some of these later season spoilers for a reason. Please do not comment character names for anything after season 1. Let's keep this a relatively spoiler-free comment section. Feel free to talk about plot points just vaguely. Okay, last one. Wounds do not heal right in 0G.
This is real. It's a concern for astronauts. If you have serious internal bleeding, bruising, that sort of thing, your body actually does rely on gravity to help blood coagulate. So it's very, very hard to deal with anything that involves broken blood vessels if you don't have gravity to help. There are also a lot of other biological issues in 0G. Many of them haven't been studied extensively because we don't have a population of humanity that has grown up in low or 0G. So some of the really long-term effects are not well studied, but certainly the idea that blood doesn't clot very well is an issue. There are studies about how protein chains are formed in low G, and there's some theories that maybe they don't form as well. Again, some of the finer details of how this happens are still being worked out. But we do know that when astronauts come back to Earth after spending a lot of time in lower 0G, they often have much lower bone density. So this is also something that kind of ties back to the general themes of the show, which is low and 0G can mess with you on a biological level. And going from low G, if you've been there for more than a very brief period of time, to high G, or really regular G, can be very taxing on the human body.
And remember, that is because humanity evolved in our specific environment, which is 1G. A species that evolved on a planet with higher or lower G would evolve based on that planet. There is no apex of evolution. Evolution does not have a direction. It is adaptations to a very specific environment. So, if the populations were separated after millions of years of after eons, a population in the belt would likely evolve to adapt better to living in the belt. However, after just a few generations, you would only see the negative effects of living in an environment completely different from the one that your body evolved to handle.
Those issues that the Belters have are not quote-unquote genetic changes or genetic defects. They are congenital issues, congenital defects, things that happen due to development in low G, not due to their genes somehow differing. I'll also note that if you wanted to create a population that could survive well in 0G, you'd have to have some pretty serious changes because, again, the issue with wounds is that blood doesn't clot well in low G. And so if you need to have a mechanism for sealing up a wound, you need something other than clotting blood.
And clotting blood is just a very small example. We need gravity for everything our body does. It is a prerequisite for humanity. A, or are we withholding a grade here?
Probable A.
Probable A. But again,
there might be a biologist in the comments who knows more than I do.
We welcome biologists in the comments to talk more about biology in low G or whether that character would have survived a spacewalk without a suit. Please let us know because those are really cool things that we want to learn more about. Thank you all so much for watching, and I hope you are just as excited for the 6th and final season of The Expanse as we are. More excited than Cece is. Anyway, have a great holiday season.
Like, subscribe, comment on stuff, I guess, if you have opinions or if you don't have opinions. Do an engagement. She's on social media, and give her money on Patreon.
Cece out. Bye. Bye, everybody. Bye.
Ad Astra, to the stars, to the stars.